Okay, so we're gonna start to work on section 6 of chapter 9, and the idea is we have a few more tests for determining convergence and divergence, and I know I've been in your seat before, so I know that this is can start to be overwhelming with all these tests. The Just continue to keep a good notebook with some and keep track of your vocabulary, and don't worry because we're almost we're almost done, right? This is the last section where we're going to have at least I think this is the last section. I've gotten so confused over this semester. Yes, but we're almost done with the tests for chapter 2 for this convergence and divergence. And this we have two more, and honestly, these are really not that tough. Okay, so the first test we're going to talk about is a ratio test, and ratio just means a quotient, right? Some fraction. Now, the condition is that we can't have we have to have non-zero terms, right? We can't have zeros, zero terms. So, but what does the ratio test tell us? Well, first let's start with what the ratio is that we're going to produce. Okay. So you're going to every single one of these is all going to have a sub n plus 1 divided by a sub n. Now, the a sub n is very easy because you're already given a sub n, right? This, like for example, this one here is a sub n. But with the n plus a sub n plus 1, then you're just going to simply substitute n plus 1 in for n. Ready? So let's do this, go through this theorem as we're working this first problem. So right now, let's set up the ratio. Ready? So let's start. Let's start by, it's a sub n plus 1. So let's go ahead and figure out. So in this case, a sub n is going to be exactly what we were given in the very beginning, which is 2 to the power of n over n factorial. And now let's go ahead and find a sub n plus 1. All right, no problem. You're just going to substitute an n plus 1 in for the n. So this is going to be 2 now to the power of n plus 1 over n plus 1 factorial. And just a little note on, and this is an important note. When you're using n, well, let's say it this way, n plus 1 factorial can be rewritten and should be written as n plus 1 times n factorial. Do you understand what I just said? This denominator, you want to rewrite that as n plus 1 times n factorial. So let's go ahead and do that right now. So it's going to be 2 to the power of n plus 1 over what? Over n plus 1 times n factorial. Okay, so I'm just gonna box in my a sub n and my a sub n plus 1. So what I'm gonna do right now is form a quotient, form a ratio. So this is gonna go in the numerator, and this is going to go in the denominator. Ready? Let's go ahead and do it really quickly. So this would be 2 to the n plus 1 over n plus 1 times n factorial. Now, I'm going to go ahead and, so normally if you were going to form a quotient, you would go ahead and have your division bar, and then you would write your a sub n down here. But for all of these, you're going to end up with a complex fraction, right? You're going to end up with a fraction over a fraction. So what I'm telling you is go ahead and do this. Instead of forming the quotient, the ratio like this, instead of having this big division bar, instead use a division symbol, because you're going to flip and multiply every time. And go ahead and write a sub n. So this would be 2 to the n over n factorial. Okay, I'm just trying to save you time. So ready, let's flip and multiply. Please, 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 you have to flip what comes after the division symbol. Not what, you don't get to flip either one. All right, so let's go ahead and rewrite this. So this is going to be 2 to the n plus 1 over n plus 1 times n factorial. Let's go ahead and change that division symbol into a multiplication symbol. And I can do that as long as I take the reciprocal, or 2 to the n. Okay. Now, this next step is optional. If you're like me, I can see that I'm going to cancel these right here. But what I'm going to do, at least for this problem, is I'm going to go ahead and write everything under one fraction. Okay. In other words, I'm going to go ahead and multiply. So that's 2 to the n plus 1 times n factorial over n plus 1 times n factorial times the other denominator, which is times 2 to the n. Okay, so numerator times numerator, denominator times denominator. Okay. And now, go ahead and follow me. I'm going to put a pin here. I'm going to put a pin here. Go ahead and follow me up here. And I'm going to go ahead and cancel the obvious. I'm going to cancel the n factorials. And let's see what that looks like. So the only thing that would be left now would be 2 to the power of n plus 1. All right, 2 to the power of n plus 1 over, well, I have n plus 1 times 2 to the power of n. Okay. So if I had x cubed over x squared, you already know that you can do x cubed minus 2. In other words, if you divide like bases, right, x is the base, you can subtract the exponents. Now, I have a like base. I have a 2 to the power of n, and I have a 2 to the power of n plus 1. So what I'm going to write is 2 to the power of n plus 1, what? Minus 1. I'm sorry, minus n. Let me write that. So I'm going to do that up here. So if I have 2 to the power of n plus 1 over 2 to the power of n, I can rewrite that as 2 to the n plus 1 minus n. Minus n. Okay, so if you drop those parentheses, the n minus the n would cancel, leaving you with just 2 to the power of 1, or just 2. Does that make sense? Okay, I hope that makes sense. Because now that this and this have simplified to 2. So let's go ahead and write our 2. So that would be 2 up here. And what's left? Well, it's just n plus 1. Now, so all of that work, so that let me go ahead and write this. So everything comes down to what the limit of this does. Okay? So for every one of these tests, you're taking the limit as n goes to infinity. So let's go ahead and do that right now. And then we'll come back and figure out, once we know the limit, we'll come back and figure out what, which one of those applies. All right. So we had So we had 2 over n plus 1. That's where we left off. And let's go ahead and take the limit with n going to infinity. All right, well, that's fairly easy. That's fairly easy. If you let n go to infinity, that's 2 over, let's say, infinity plus 1, if you'd like. That's $2 chopped up an infinite amount of ways. That means it's equal to 0. Now, our goal right now is to figure out, and I hope that you can see this. I think maybe I'll see if I can make it a little bit larger for you. So our goal right now is to figure out which one of these tests, or what conclusion we can draw, if any. So here's what it says. So first off, if you take your limit and it's less than 1, you get to make a statement. If you take your limit, like we just did, and it's greater than 1, or if it's equal to infinity, you get to make a statement. And if it's equal to 1, you don't get to make a statement. Let's read. So if your limit is less than 1, then you get to say the series converges. Now, to say that it converges absolutely basically just means it converges with or without negative terms, okay? But so it converges if the limit is less than 1. If the limit is greater than 1, or if the limit is equal to infinity, then you say the series diverges. If the limit equals 1, the test is inconclusive. With me? All right, so let's go ahead and draw our conclusion. So in our case, we have a limit equal to 0. So since 0 is less than 1, we are going to be, right here for the first part, 0 is less than 1, so we get to say it converges. So thus, the series converges by, I keep writing by, and maybe you're just thinking that you don't need to express how you know that it converges, okay? By ratio test. You have to tell me why. I have to be able to separate the student who takes a guess, converges, diverges, right? Binary, it's a binary proposition. I have to be able to separate the student who arrives at the correct answer for the right reason or the wrong reason. If you just say converges, I just say, because it's a meaningless statement. Maybe you guessed. Ready? Let's go to ratio test, the second one. All right. So what I'm going to do, let me go ahead and make this a little bit larger. Again, hang in there, hang in there. There's only two more tests. I mean, this is the first one. Only 2 more tests that you need to know. So what I'm going to do for you is I'm going to go ahead and set this up for, maybe we'll start with just A here. I'll get it a separate page. So let's go ahead and establish that obviously A sub n is equal to whatever you were given. So n squared, let me write this a little bit larger, is equal to n to the power of 2 times 2, and notice that this is all in the exponent. Let me make sure that this is expressed, times 2 to the power of n plus 1. I can just see a student I can see a student thinking that's 2 times n plus 1, right? All right, over 3 to the power of n. All right, now we need to find out what a sub n plus 1 is. All right, so we got to plug in an n plus 1 here. We have to plug in an n plus 1 here. We have to plug in an n plus 1 here. Ready? Let's go ahead and do that. So this is going to be n plus 1 squared times 2. Now you can go ahead and do this in your head, right? Because 2 to the power of n plus 1 is basically what you would have there. But so that's going to be, let me make sure I did that correct. Yeah, so that would be n plus 2. 2 to the power of n plus 2 over, well, 3 to the power of n plus 1. All right. So you have your a sub n, you have your a sub n plus 1. Let's form our quotient. I'm going to go ahead and flip and multiply, right? Because you know it's a fraction, you flip it and multiply it. So let's go ahead and write it. So this would be n plus 1 squared multiplied by 2 to the power of n plus 2 over 3 to the power of n plus 1. Now, I'm going to flip and multiply, so this is times 3 to the power of n over n squared times 2 to the power of n plus 1. Okay, so you can see that this is not bad. You just got to be able to notice the ways that you can rewrite. Like, you don't want to take the limit of this, right? You want to rewrite that. So let me change my color here. So let's notice that we're going to have 3 to the n, right? If we have n here and n plus 1 here, that's 3 to the n minus what? Minus n plus 1. We also have 2 to the n plus 2, now minus n plus 1. And let's go ahead and tackle that right now. Okay, so for each of those, let's go ahead and rewrite that. So that's 3 to the power of, let's go ahead and do our arithmetic. So we'll have n minus n, that'll cancel. And then this is a negative 1 basically distributed to a positive 1. So that's going to be, or change the sign, however you like to think about it, that's going to be a negative 1. So that's 3 to the power of negative 1. Right, or 1/3. All right, let's go ahead and do the 2. So that's 2 to the power of, let's go up here and think about it. So when you change your signs, that's going to be a positive n combined with a negative n. And then we're going to have a positive 2 minus 1. So that's 2 to the power of 1 is what's left, or just 2. All right, let's go ahead and rewrite this guy now that we've done a little bit of work. So we didn't do anything to our n plus 1 squared. We left that alone. So since we also have a 2 to the power of 1, that's 2, so that should be, I'll use that a different color. So we should now have a 2 up here. We didn't do anything to this n squared, so we'll still have an n squared down here. But we did figure out that that's going to be multiplied by, that's a 1/3. So 1/3, meaning 3 is going to be in the denominator. Okay. So I'm with you, a little bit of work, but that's not bad. And now it's time to take the limit with n moving to infinity. Okay. So the best thing to do here is to you're welcome to FOIL that out if that helps you. But what you would do in this case is you would end up using L'Hopital's rule, okay? And so you would take the derivative of the numerator, derivative of the denominator. You might have to use it multiple times. What you will get, and I will let you work through that, but what you will get in the end is 2/3. How did that become 2/3? Because you used L'Hopital's rule here. You took the derivative of the numerator, derivative of the denominator. If you needed to do it again, then you did it again. If you needed to do it again, you did it again. You did as many times as you needed to till you got to 2/3. Now draw a conclusion, right? You've been talking, right? You've been arguing for a long time. Now conclude your argument. Therefore, right? Well, 2/3 is less than 1. So if you look back on your previous, in your notes, what does that ratio test say about when your limit is less than 1? It says it converges. Therefore, converges by ratio test. All right. So what I'm gonna do for part B is I'm gonna give you the answer, right? Now you're either going to write this answer and just assume that you could get it if you, or you're actually going to take time and make sure you can produce the answer that I produce. And then if you can't, then you're going to come see me during office hours, and I'm going to help you. But you end up with, after all the simplifying, you end up with the limit with n going to infinity of 1 plus 1 over n to the power of n. And do any of you, because I can hear you, do any of you remember what that limit is? Oh, can you say that louder? What was that? Oh, that's e. Ah, okay. So, and what is e? Well, right, e is just a number. It's a number on a number line, and it's larger than 1. That's all that we care about, right? E is greater than 1. So this one diverges by ratio test. All right. So let's let that conclude our ratio test. Just remember that if you were to get 1, you do your ratio test and you get 1, you have to say it's inconclusive. You have to be able to say the ratio test does not work. Okay. So we'll go ahead and conclude this, and for part A, part B, we'll do one more test. Again, not that bad. It's called a root test, very similar to this one. And then we'll, for the most part, be done with our tests. It gets a little bit better. There's light at the end of the tunnel, so stay with me.